Alrighty, hello, my name is Daniel Lunsford, and this is my Physics2212 Lab 4 Circuits lab report. So for the introduction, the purpose was to utilize the principles of current and conservation of energy through criteria set by the loop rule, the definition of steady-state circuits, and then predict and examine the behaviors of RC circuits with ohmic resistors and capacitors, and then to utilize multimeters to record and calculate values related to the circuit. Here are some of the fundamentals we used, which consist of the node rule, the loop rule, capacitance, and time dependence in RC circuits. So the results from the experiment were that the predicted values given by the sets of equations used match the values that we found experimentally, and in an RC circuit the magnitude of current is time dependent based on exponential equations. So for models and assumptions, the model was using a supply of simple circuit elements such as batteries, wires, resistors, capacitors, light bulbs, and a multimeter to observe the behaviors of resistors and capacitors in a circuit. And some of the assumptions we made were that the resistance of the wires and the multimeter were negligible. And for the experiment, the system was circuit, surroundings, everything else. For part 1, we used a circuit with two 1.5 volt batteries, 2 resistors, and 2 multimeters. Our predictions were that I2 would be equal to I1 by way of the node rule. The total ohmic resistance was 147 ohms. Our calculated value for I was 0.02 amps. And then we were to replace the ammeter with the voltmeter readings, and from that we got 3 volts with a calculated value I of 0.02 amps, it should be. And then no current and potential difference across the opening equals that across the power source. So for the experiment continued, we were then to measure the potential difference across each segment of our circuit. And here are the measurements we took. And then the delta V round trip was 0, which follows the loop rule. And our I was 0.02 amps as expected. And the ammeter reading doesn't really change because the voltmeter has very high resistance, meaning essentially no current flows through it, and the path of the current in the circuit remains unaltered. Here's my graph. Experiment and observation continued. So we were then to connect the ammeter in parallel with a 100 ohm resistor, and the current reading increased to 0.06 amps because less current comes into contact with the resistor since it splits at the node, and since the ammeter has 0 ohms of resistance, the effective resistance of this portion of the circuit decreases, ultimately increasing the current since I equals delta V over R. And here are the calculated resistance values, which were higher than expected due to a low precision of the ammeter. Then for part 2, I did on the CCK simulator. I used a 10 ohm bulb, a 20 ohm bulb, 9 volt battery, and a 200 millifarad capacitor. The battery was connected to the 10 ohm bulb and capacitor in series. The bulb starts bright, then decreases until going out, and then I disconnected the battery using the charged capacitor to light up the bulb, which lit up and then decreased until going out. And then here are the time values for the 10 and 20 ohm bulbs. So here's my slope calculation, which is -1 over RC, which came out to be 0.167, or just 1 over RC, which is 0.167, using the equations at the bottom. And some model discrepancies were potential issues with part 1 using the multimeter, general atmospheric surroundings, and material issues. And some sources of error were human error when reading multimeter values and error in circuit setup, and then just old batteries and equipment resulting in inconsistent voltage. And what if you were doing this lab online and used an ideal simulated ammeter? What's different about a simulated ammeter, and how would it have affected the circuits you hooked it up to? An ideal ammeter has nearly 0 resistance, so our current values would have been more accurate compared to what the theoretical approach states. And then for part 2, I did it on the CCK simulator. So what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict a capacitor to reach full charge? Would this prediction happen in real life? So if I had done this part using real circuit elements, The capacitor likely would not have charged instantly, and the model predictions likely would not be entirely accurate due to model discrepancies and the general environment. Alrighty, thank you.